Good afternoon, everybody. I have prepared an official statement for this. Welcome to Airtime. This is the second talk in the series. This is something Berkeley and Crown have put together. And last week we started off with Alex Bryan, Professor Bryan from Berkeley. This week we have Professor Raja Sengupta from Berkeley. Well, Raja has a very phenomenal history at Berkeley. He's focused on automated cars, he's focused on parking, he's focused on drones, he's focused on aircraft, now he's doing public health too. So has a very spectacular, body of work, and he has brought some of that to share with us today. He likes to do research in the industry and get it into marketplace. And he also holds several car-to-road networking patents with Toyota, a UAV patent with BAE's Aerospace, and car-to-car networking contributions standardized by ICE. I like to put it in this way: when professors really think of talking to people, we get rusted. Yeah. So on that note, I would like to welcome Raja to share his work today. Please join.
I would say that, professors, I always say that, I have to speak from there?
Yeah.
Okay. Are there people online?
Yes.
What people online?
How would you take the question?
I can take them as they come. That's fine. It's fine to interrupt me. But I'll see who's asking questions. If somebody can monitor the chat and
I'll monitor.
Stop me, that would be great. You're of course welcome to stop me physically. I sometimes say to myself, my product is actually not aircraft, it's not advanced air mobility, it's people. Professor's introduction is actually students. And in that sense, I feel quite honored. I know several of you, and looking forward to meeting some new people today. And it's a great pleasure to be here. So with that, I want to talk about advanced air mobility. Right, it's what I've worked on for a few years, and I've sort of fallen in love with it greatly. And this work is all collected together in the Aviation Innovation Research Lab. And it's very complicated to get that, because I have to stand and talk here, right?
There or just in this general area?
I think I'll say and talk here, because this is probably best for the cameras and audio and all that. So why don't you do my slide?
Okay, sure.
Right? We'll just keep it simple. And Vishwanath knows the talk, and he can answer. Okay, so this is joint work with a number of people, and I would say the first among these people is Min Shu. He's out here today, but a lot of this started. Actually, I think all of it started with me. And this was several years ago, and then Anil Chakrabarti, when he was at Supernal, was my program manager, funded some of this work. So some of the work is OEM funded, and then of course there's my colleague Mark Hansen at Berkeley, and Vishwanath has been a friend, a philosopher, and increasingly a guy in this work, because he's in some ways so much better informed than me now from being part of NASA Ames. And then there are, of course, my students. Albert is still at Berkeley. He should be finishing next year. Amin is in the NSF ICOR program, decided to start a company doing some of this stuff. Shwan is at Google Cloud. Pavan is at Whisk. Shin is at GE. And Jean-Luc is at Berkeley, sharpening his claws. So with that, Vishwanath, the next slide. So there are, there's over the years with these PhD students, we built up a set of tools, and two of them are simulators, VERTISIM and LPSIM. There's some large-scale simulation problems. We built up stochastic control for vertiports to control surface operations, airside operations, dispatch, charging. And so there's a lot of reinforcement learning. And so these simulators are also used to train the reinforcement learning. There's demand shaping that we do in order to understand demand for, the use cases. The airport use case in particular is something that we focused on a lot. And you can see, there's asymmetric demand. All that has implications. We do fleet sizing for aircraft. There's a lot of analytics we've developed for vertiports. So there's simulation, of course, that happens in VERTISIM, and then There are queuing theoretic models that we built where we write balance equations, solve them, and that allows us to do easy trade-off studies. That for a particular sort of demand, should we put 2 TLOS, should we leave it as it is, etc., right? And then of course there's some work on air corridors, which was particularly important when we were looking at LAX. Next slide, Vishnu. These papers are all on the AirLab website, air.berkeley.edu. I think Vishnu came up with the URL. We're particularly proud of it. What could be better? Aviation Innovation Research Lab. Next slide. So I want to talk today about 3 networks, right? And I think that's the way I've been thinking about AEM from the network standpoint. It's a field with a lot of brilliant people, and so it's sort of important to, do something very specific in this field and add value. And I think this is the way I thought it. So the first network that I want to talk about is centered on LAX. There are 8 vertiports around in different city centers, and we're looking at transportation to LAX, right? So that's one, and out of LAX. The airport use case is a good one to focus on. This little graphic here has, talks about the willingness to adopt AEM for particular use cases. And the airport use case is this color here, right? That light blue color, the last bar on the bar graphs. And you can see that, the idea of using an air taxi to get to the airport has acceptance. The other thing about the airport market is people are willing to pay a lot of money when they will need to fly to the airport. So Uber is able to charge people as much as $5 a mile in many markets, and over $4 a mile in every market that we've looked at. Next. The second network that I want to talk, so the network 1, the LAX is an eVTOL analysis, right? Network 2 is actually the regional airports, and it's with CTOL aircraft. And the aircraft are a bit, they're not studied in as much depth as we looked at, and I'll explain why. But the idea is that we network these regional airports with the road transportation network, right? So we study the interface actually quite carefully, and then look at what is the value of the regional airports. In this particular network, I focus on the Bay Area and the 24 regional airports that are in the Bay Area. And as the student of mine likes to say, we're trying to take what's a patchwork of airports and convert it into a network and understand the value of turning it into a network. Next slide. And the third network I look at is the San Francisco Bay Area again with very large numbers of vertiports, right? And to see, basically, do large numbers of vertiports actually generate value. If we go to the next slide, it actually, I think, tells me what my sort of focus in, previous slide. It tells me my focus in these networks. So the first network is very much, it was OEM funded, and so very much sort of what is the return on investment, right? Are these networks actually places that we can actually run a business as an OEM? How many aircraft would we expect to sell for a particular market? The second one is actually very motivated by NASA's regional air mobility study. I did, and then network 3 is, if you did build really big networks, vertiport networks, do they actually have value? Or is there some diminishing returns beyond a certain number of vertiports in an area to understand that? Okay, so next. So my methods, right? I thought I'd have this. So one of the sort of important things when you want to take an aircraft network and integrate it into the ground transportation network is that, when you're doing urban air mobility or regional air mobility, let's say under 200 miles, right? The first and last mile are very important. And actually later I have a little extract from the NASA program manager for the Small Air Transport Network, or the SA Small Air Transportation System is, I think, what NASA called it in 2006, etc. And you'll see that this is very well written. Like, when you're flying San Francisco to New York, you don't so much care about the fact that, it takes me 1 hour to get to the airport and then another hour to check in at the airport. And then I wait another, 30 minutes at the gate. And it's all good because the alternative is 3 days to drive to New York, so you just don't worry about it. But when you fly San Francisco to LA, you do worry about it because the alternative is to drive 6 hours. So once the whole thing crosses 3 or 4 hours, you start to say, I get there and I'm without my car. And if you're doing 20-minute flights, it matters a lot, right? So when you do this, it's very important between the road network and the air-com road network to reach some kind of convergent fixed point. When you take a group of people and you put them on the air network, and then the roads actually get better because you move them. And so, well, you need to move them back because now it's no longer good to go by air. So you need to run these simulations till you reach some kind of convergent fixed point, or what transportation people call an equilibrium. And in order to do that, if every simulation takes 15 hours, you can't do this, right? So one has to speed up that whole thing. The next slide we should up. And so, one of the things that, we started with Min, and then we realized this problem. And at that point, we were saying, well, why don't we just ignore 90% of the demand? Because, we can't actually simulate so many people. And then we'll just multiply the results by 10 and, it sort of make claims. And that's the way we did things at that time when Min funded us. But in the ensuing years, and he was doing GPUs at that time, actually. He was writing a simulator for the air taxi aircraft. And I actually got the whole GPU idea from him. But today, after all the work that Schwan did, we can do this. So if you want to simulate the whole San Francisco Bay Area, the red circles there are some of the airports, and the blue is showing you the congestion on the roads, and etc. You have to simulate about 20 million trips. And we can do this. That's 24 hours at the Bay Area. We can do this in 20 minutes for $16 in the cloud. That's what every round costs. So you run 100 simulations, which is typically what you would do to get a convergent fixed point. You've spent about $1,600, right? So that's cost. It's multi-GPU, and compared to what was there before it, that we speeded up by a factor of 100, right? So it was 20 times 100 minutes. It was a big problem. Okay. What's the level at which I model aircraft, right? This is NASA. It's important to be precise about that. So we model aircraft at sort of this trajectory design level, right? But there's no sort of trajectory conformance and feedback control and all that, right? Because I'm trying to do very network level studies. So I do model these different phases, and this is for an eVTOL, and because and then we designed this part for for the flight route, with its curves, et cetera, right? We put different waypoints and things like that. There'll be holding fixes and things along the route when you're trying to get into LAX, right? So all that is there. And then we compute the energy consumption, depending on that trajectory design and the holding times and all that, right? So all that varies. The other thing that we do model the nonlinearity of charging, right? So what you ideally want to do is keep your aircraft operating in this point of charging. So the optimization method considers these nonlinear models and therefore does not push things here. And this you can do if actually your flight distances are short, right? If you have to fly long flight distances, then you do have to go in there and things become a problem. But in some of the networks I've studied, that happens. But in the results I'm presenting today, you're able to keep the fleet operating here. Okay, next. We model demand, as I said, right? So for example, with LAX, we basically look at the taxi and rideshare market. We assume that's what the air taxi is going after. And there's, and then we look at the arrival and departure patterns, from SPM data. And that's what we use to shape the demand. So this is, for example, from downtown LA to LAX. And you can see that, the demand varies with time, and it's also not symmetric in two directions. So this results in deadheading flights, which increases costs, et cetera, right? So all that shows up. And then, we'll basically look at, when I'm studying the network, there's data available on how much of the airport traffic comes out of which zip codes, right? So we're able to do that. We place the vertiport, in, let's say we're looking at downtown LA, or we're looking at Hollywood. We'll place it, we just assume we can place it somewhere in the center of the city, right? We didn't try to do it as carefully as you did, right? So that would be a second thing. And then we sort of, just sort of assume that the demand is distributed about Hollywood, and we compute first and last mile times by, for our data by spreading them randomly, et cetera, right? So that's how we do all that stuff. And so this is the total passengers. What's the share of, so that's the market we're going after. What's the percentage out of the downtown LA zip codes? What's the average Uber fare, et cetera. Next slide. And we do, so as I said, we assume we're competing in the taxi and rideshare market. And then what we do is we actually optimize the UAM pricing to increase the operating surplus. And so our pricing is actually becomes variable by time of day. It's different in different markets, as you'll see, right? So we actually initially we did lots of stuff with fixed pricing at $3 a mile, like Jody said, but then we moved to variable pricing, and you'll see that it becomes important, right? And on the road side, on the Uber side, which is what we're competing with, costs vary because we consider how much you pay plus the time that you put in, and we convert it with the time value of money. The monetary value of time, right? So that component varies. So we have not actually modeled Uber search pricing and all that, right? So, I mean, in a lot of this, you'll see that there are things we've done. But if you really want to put all this together and do everything comprehensively for a use case, right, in a way that you can actually base investment decisions or policy decisions, I don't think we can do it at a university. So the spirit of my talk is very much methods. But if we're going to do this properly for policy, we should do it at an organization like this, or do it at a company or something like that, right? So next. Okay, so in order to do our CapEx, so we take this demand, right? And we say that, okay, people should not wait more than 5 minutes or 10 minutes. So there's a stochastic process that generates demand as per the LAX data and all of that. And then we say that, if the aircraft, if there are 4 people waiting, they're 4-seater aircraft, then dispatch an aircraft, right? Or if somebody's waited 5 minutes, right, then dispatch an aircraft. Even if it's one person, just dispatch an aircraft, right? So we do that, and so that becomes the demand schedules, and that's what goes into, we solve a vehicle routing problem with nonlinear charging time. And then, and that actually gives us, the next slide, these kinds of parameters. It gives us the fleet size, right? We sort of do the fleet size so that we don't try to serve 100% of the demand, because the demand is stochastic, and you never want to make your capital investment for 100% of the demand, because it'll have good utilization. But we basically size to about 87 to 90% of demand. Right? That's what we size to. So on a really, really high demand day, there is a significant amount of demand that gets spent. So that's what it ends up being. And then the other part of that the CapEx gives us is actually, in order to sustain operations, how many charges do I need at each vertiport, and how many TLOFs do I need at each vertiport, right? So it gives us things like that. And then that becomes the way I can compute CapEx, because we've done it 2 ways. One is we've looked at the cost of land. I think it's based on the cost of land. The other way we've done it is look at the cost of parking. So what is the cost of parking in downtown LA? And we'll say, okay, if your vertiport is this many square feet, once I've got TLOFs and chargers, I can use the FAA design brief to work out the square footage. And then once I have the square footage, I'll say, okay, this is the cost of this many square feet of parking if I was building a parking garage, and that's going to be my capital cost. Right. Okay. Then, yes.
So in your previous slide, can you go to the previous slide? One more. So in this, you said you wanted to keep the charging time to say maybe 10 minutes or 15 minutes, 20 minutes or something. Is that what you said? You wanted to keep it within that?
Yes. So what happens is the optimization does that. Right?
Well, I'm trying to relate that to what range do you get from that?
What range do I get from that? I think in my extra slides.
Limit your trip, right?
So in this market, right? I think the largest flight time is 25 minutes. I've got a slide with it later. Okay, that's the longest flight time. There's nothing above 25 minutes, if I remember correctly. Okay. So, and the distance, I think, corresponding to that is probably about 20 miles, right? It's not more than that. This case study is based on the Joby S4, the model that was published by Shripad and Vishwanathan out of CMU, right? So if I do a trajectory design like that, for every phase, they give me the energy equations, right? So So I'm looking at a 150-mile aircraft doing 20-mile trips.
Yeah.
Right? And because the optimization accounts for the high cost of charging to full SoC, there are sometimes at night when it does that. Right? But in the main, the optimization just avoids charging to full SoC. Okay. Thanks. Yeah, so once I have all this, then I move to operations, right? So I run all these simulations where I generate random demand, right? And our modeling of LAX demand actually includes seasonal variations in demand, as well as diurnal variations in demand. So I actually have a 365-day model of demand coming out of an airport like LAX. Okay, and that's what goes into this simulation, this VERTISIM simulator. If you press it, another key will run, I think, or the movie will run. And basically, the interesting thing here is, this is higher fidelity modeling of what is going on in a vertiport and the aircraft and holding and all of that. And, what's interesting is that the three flows, energy, people, and aircraft, have similar time scales here, right? It can take 10 minutes to charge an aircraft. If people wait more than 10 minutes, they can get upset and say, I'm not doing your service. That's the magic number with Uber. If it's less than 10 minutes, then people say, sure. If it becomes over 10 minutes, my Uber wouldn't come today, right? And then, of course, flight times can be 10 minutes, 50. So very, very comparable, right? Whereas, in legacy aviation, it's quite different. So, okay, next. Oh, sorry, just go back for a minute. Well, we'll have to start with that movie again, but that's okay. It produces a lot of statistics. Your aircraft hours, how much of each aircraft, how much time was spent charging, how much time was spent flying, how much time was spent, it does all that. There's a lot of analytics that it produces. But let's move on, Vishwanath. And then because I have a simulator, right, and I have demand modeling, and I also actually have stochastic wind models, right, which we built because that actually has a significant impact upon energy too, in this market at least. And so we use, these are the two sources of uncertainty, and then I train reinforcement learning, essentially, which controls two things. And, at a particular time with an aircraft, should we charge it or should we dispatch it, right? And then, of course, with the TLOF, right, that, there's an aircraft waiting to land, an aircraft waiting to take off, what should I do? The decision, because of the energy model, is invariably to let the landing aircraft land, right? Because, we sort of model like cycling behavior, but it's reasonably tight cycles and it does consume quite a bit of energy. Right? So that's, and then the penalties that it's in the cost function are passenger waiting time, because if they wait long, they'll spill the passenger, there's a penalty for spill, and energy, right? These are the important things that it pays attention to. The AI does improve on Uber Elevate, right? So that's a good thing. The Uber Elevate was quite a few years ago, so all this stuff has actually been worth it. We're almost 10 years later. We get a better load factor than Uber got in what it studied. They did DFW, and then our repositioning flights are also quite smaller. The deadheading percentages are also significantly smaller when we do all this optimization. The operating costs, these are the things we've considered, right? I don't know how much faith I should have in this, as I sort of said, we can put numbers to these things in, but I do not want to thump the table here and say that, I've got the right numbers, or even I've got, the right costs, right? Because as I say, that if you really want to do this properly, these are optimization methods. You can put numbers in for this. You can even add more costs and be fine. But if you really want to do this thing comprehensively, it needs to be done. Yes.
And you look at the cost of vehicles.
Yes. So in our CapEx, right, when I do fleet size, I do cost of vehicle, and I use the 1.3 million number from Joby's SPAC filing documents. So the CapEx component is mostly those two things: cost of aircraft and cost of vertiport. Small aircraft transportation system. I really like this paper. I feel that I don't know who this person is, Guy Kemmerly. I don't know where he is, but he's written really well. He's written here that above 1,000 miles, the air transportation system does a great thing, but below that, 300 miles, 400 miles, 500 miles, we worry about all this stuff. And when cars are under 3 hours, is what he says. I think he's right. We're fine with it. But the moment a car trip becomes 5 hours, we start, should I take a plane? Then you get stuck in the middle. Should I take a plane? Should I take a car? Should I take a plane? Should I take a car? Right? Would there be a better solution? And I think a lot of this is worth looking at. The other thing I wanted to put a slide on, I've got it somewhere in my extra slides. I didn't put it in. At some level, this stuff has happened before, right? There was the Los Angeles Airways, there was New York Airways, there was the San Francisco Oakland Helicopter Company. They all went bankrupt. Right. And my colleagues, Adik Kanani, old timer at Berkeley, tells me, Raja, you could take a helicopter from the Berkeley Marina to SFO. Right. You can't now. I believe New York Airways and Los Angeles Airways went bankrupt after 2 spectacular accidents. I think the New York Airways helicopter fell on a helipad on top of a roof and killed 3 or 4 people, then fell off the roof onto the street and killed another 6 people, I think. And that was the end of that, right? So all this has to be thought about. I am on the side where I believe that we try a new technology, we will have accidents. Somehow or the other, the industry has to survive its accidents. And anyway, that's okay. So next, results. Let me just check on doing for time. Okay, seem to be doing okay. All right. So network 1, right? LAX, eVTOLs, 4 seats. Next. So here's how things look, right? So one message is that, when you do all this price optimization, time varying price, adjust it to the market, how much is Uber charging in this market? I got to compete with it, right? When you do all that, we tried the $3 a mile, we tried the variable pricing. And if you want to study a market and model how these operators are likely to behave, I think this is the better thing to do, because it produces significant differences and greater returns on investment. And so if you're going to model, airline behavior in this market or something like that, this is probably the way to think about it. There are small differences in fleet sizes, number of TLOPs. This is for the whole network, these numbers, right? Number of TLOPs, number of charging pads, etc., chargers. But the capex is very similar at the end of the day. There is a significant reduction when you do variable pricing in the number of flights, right? There's a very significant reduction. This is 1,104 revenue flights and 235 repositioning flights, deadheading flights. Number of aircraft hours is not that different. There's a significant drop in the number of passengers when they actually do this variable pricing. And I think, airlines in legacy aviation like to speak about revenue per available seat mile, right? But here, in this market, at least, because distances are not very large, flight distances are not very large, the aircraft, I think, spends a lot of time taking off and landing and transitioning and stuff like that. So revenue per aircraft hour is actually a better way to think about this. And here, even though the number of flights is less and the number of passengers is less, the revenue per aircraft hour is substantially larger. Right, and we use a probabilistic mode choice model and all that, that's calibrated, but where the traveler looks at the cost of taking an Uber, the time of an Uber, the cost of that time, the cost of taking this eVTOL at the price that I've set, the first and last mile cost, that's also taken into account. The first and last mile time is taken into account. The flight time is taken into account. Transition time is taken. All that's taken into account, and makes a probabilistic choice. Right, using the conventional methods that are used in travel demand modeling, what's called a logit choice model. Revenue per seat mile is very similar. Load factors are slightly lower. We're flying less people, but the daily revenue is substantially higher. Right, because in certain markets, I'm just charging. So, for example, if you actually look at the breakups, and I kept results high level, if you do this fixed pricing, in the Anaheim LAX market, which everybody's very interested in, right? The Orange County, Disneyland, Anaheim LAX market, it's really not worth flying because the distance is actually quite large. That's the largest distance I've got, I think. But when you do variable pricing, it turns out that they do it says the operator will do a lot of flying in that market. because it's very competitive. Longer flights do result in economies of scale. I think that's what's going on. And, so this is the total aircraft miles flown with this variable pricing is substantially larger. And that's mainly the Anaheim market that's kicking in. The revenue aircraft miles is also larger, though the number of flights is lower. And so you see it sort of produces these important differences, right, when we do this. Yes.
So two questions. In the previous one, you said the number of passengers went down and the number of flights went down,
Yes.
but your revenue increased because you were charging a lot more.
I'm charging a lot more and I'm flying in these longer markets. Yes.
In the demand market.
My aircraft miles have gone up. Yes.
Yeah. And you're saying the battery replacement cost is lower with higher number of takeoffs and landings. Your battery replacement cost should actually go up.
Per available seat mile. Well, seat mile. So available seat miles
That
would be here.
Yeah, your number of passengers went down.
My number of passengers went down,
So available seat mile.
but my number of miles went up.
You stay the same, but your miles might go up.
Yes.
Yeah.
So, there could be something problematic here, right? It's a complex picture and there could be.
So my read on it is that, look, for your longer trip market, you're running less battery cycles. For shorter trips, you're going, charging again. So charging many times kills the battery faster than charging.
Yeah, I would also say the
So on the
following.
left side, you're charging many times. On the right side, you're charging less, but using a lot. Your single cycle is longer. Like imagine going from here to Mountain View.
The demand is only from Anaheim to LAX.
Yeah,
That's one of the routes on the network. Isn't
I
it?
would not try to sort this out now, as I said. Right? There is a possibility that there's something problematic here. There always is, right? In any case, I would also say that, the student wants to put in battery replacement cost. It's a significant cost, and he's done that. But the whole battery replacement thing is one of the big questions that is facing the industry, right? Like I was at this OEM meeting somewhere in Southern California last year, and they were all like, we want insurance for our batteries because it's so unpredictable. And then who's going to insure these batteries, right? So that's a market apparently that doesn't exist these days. People don't insure battery. Insurance companies don't insure batteries. Right, so I think this is one of the big gray areas of this field, and I'll take a look at that more carefully. Okay, as you pointed out. Okay, and make sure.
May I ask a question? Sorry, I'm online.
Yes.
These results suggest a perverse incentive where the right business case would be to only step in with operations on a few routes for a few flights when there are the most travelers. Because the airline industry today is much more focused on providing complete coverage, routine flights. But in this regard, it looks like if I was a small operator, it's like it's just like Uber. Like we have a whole bunch in the Bay Area. We have a whole bunch of drivers coming in from the Central Valley only when it makes sense for them to actually conduct their business, rather than having a network of providers that are always available. And then if that's the case, then what does that say about the viability of this replacing, if I want to go to the airport and all of a sudden I find out it's not, no one's available, then I'm still back to getting to the airport the traditional way.
Okay, so let me respond to you in two parts. Maybe I should be near the microphone, right?
Mhm.
Let me respond to you in two parts. So let me take the last thing that you said first, right? That okay, this is what these people are going to do, and now I'm going to go and it's not available, right? I wouldn't draw that conclusion from this modeling, because this modeling doesn't get down to the level of, are you just doing this service, you know, you arrive at the vertiport and then you see if it's available and you go, or are you reserving in advance, right? So we really haven't gone down to that level, right? So, you know, that uncertainty, maybe the way all this demand is being generated is by an operator that actually accepts reservations. Right? And there'll be some reservation policy, which we'll have to manage, because the reservation policy will have to model the uncertainty that the operator will face and all that. Now, the first part of what you said is actually, I think, very thoughtful. I did not spot that parallel myself, but you're absolutely right. If you go and talk to the city of San Francisco or the city of Berkeley, or they will complain about this. That the TNCs are present in the high demand, high value markets, but there are all these other markets where people don't have that high willingness to pay, and they will not go there. Those markets also often have poor bus service. So, cities look at this as a problem. And I think what you're pointing out is this analysis is showing that air taxi operators may behave the same way. Correct?
Yeah, thanks. That's helpful.
Yeah.
And I think you're right. A reservation system, in some regards, would alleviate at least some portion of
Yes.
the effect, because they could bank on there being demand.
Yes.
That
But there
will
is a separate
materialize.
policy issue here, right? And I'll say something at the end if I have time about pricing of how things should be done. But let me actually move on, because it's 11:38 now, and I have a couple of other results to get through, and I don't want to go till the last minute. Here we do look at airspace load, right? So number of aircraft in the air is never more than 30 aircraft in this whole 7-city and LAX area. Time between takeoffs at a takeoff. The busiest one is, of course, the LAX takeoffs. And it's always greater than 3 minutes between takeoffs. But there are landings in between the 3 minutes. So things are tight. You can see the numbers of flights, they're in the hundreds. You can see the numbers of passengers. My sense looking at, this market, this 8 vertiport LAX market, is so this gives you the UAM time, right, which accounts for transfer time, first mile time, last mile time, etc., and flight time, and then the driving time. The travel time advantages of the air taxi in this market are fragile. And so I do believe that in this market, the wise way to proceed is to enable this market by allowing TSA clearance at the vertiport, and provide the air taxi service with a fundamental advantage in that sense. Otherwise, I think the travel time stuff is a very risky game to play in this market. So the OEMs are very focused. So this is actually, you can see the flight times here. The largest number is 25 minutes, right? That's what I was saying to you. And we're actually looking at this call. Right, because I'm flying everybody. I'm not flying from Anaheim to WDH. I forget what WDH is. It's one of the airports. Burbank or I forget. That's 25 minutes. But this LAX thing, the largest thing is 15 minutes flight time. So this market is short, and this is how we model egress time, ingress time, waiting time, and first and last flight times are actually 50% or more of the total UAM time. So that's pretty important, integration with the non-air transportation system. In system 2, right, conventional takeoff and landing, I was looking at traveler and system value. There are 18 million travelers here. That's data from the San Francisco County Transportation Authority. And what I do, let me explain. So what I do actually, I take these 18 million travelers, and for each of them, I construct an alternative. I say that you're going to go to an airport that I choose. Okay, you're going to drive your car to an airport that I choose. You're going to park your car. Then you're going to fly from that regional airport to another airport that I choose. And then you're going to Uber to your destination. Right? And If it saves you 20 minutes or more, you're going to do it. Okay, it's very simple-minded in that way. Not as sophisticated as the previous network, very simple-minded in that way. Next slide. And now it turns out that if you look at the Bay Area 18 million trip data set today, right, it turns out, you do this, you can save 230,000 people 20 minutes or more. That's 1.3% of my regional demand. And that's about as many people. The BART serves about 250,000 now. It was more than that. It's about 2% before the pandemic, but the BART is about 1%. I mean, something like that, 1.5% of the Bay Area, right? So this was basically trying to understand. Everybody thinks that these regional airports are in shit places that nobody cares about. But this is not true for 230,000 people, right? And that, to me, is important. Next. I actually do this, right? I do this by optimizing, by building a fleet with a heterogeneous mix, which goes all the way from 90-seater aircraft to 3-seater Cessnas. And this is the at Reed Hillview Airport. And you can see that, you know, in the hours of the night, all these small aircraft are moving. Every dot is a flight, right? And you know, later in the day, there are all these big aircraft flying, right? And if you want to sort of understand what the flight frequency is, so between like 5 a.m. and 10 a.m., there are 85 takeoffs across these 24 airports. Okay, next slide. And this is the fleet mix that I come up with. It's an approximate. It's a heuristic optimization. It's not an exact MILP solve, but it says, like, you know, for this Bombardier, you know, I have like 19 of these 90-seater aircraft in my fleet, and you know, I got 28 of these Cessna 172s.
So are you still assuming these CTOLs are electric or?
No. I just assumed, I did all the flight times and all that exactly with the jet fuel Bombardier 90.
I'm sorry, I'm just having a very hard time swallowing your premise that you provided here, that 230,000 people can benefit from what you're suggesting.
Well,
It's
there are 737s that fly 35 miles in this country. From Milwaukee Airport to Chicago O'Hare. I can
yeah,
this next slide.
that's.
I'm not trying to say that we're done. Let's you and me start a company and buy 19 Bombardiers.
I'm with you, because I do it's financing.
Right?
Here too. You got the big man here.
But let me get to what I do want to say. Right? I mean, next. Okay. Moreover, the ground air interface is actually really, really important. At many of these airports, I can actually move more people, and there is demand. What happens is the roads into the airport are not big enough. The queues at the traffic light get large, and my 20 minutes vanishes. Okay? So if you want to move more people, you should actually build bigger roads into these airports. The runways are not the operating constraint here. Next. So here's, you know, kind of what things look like. If you look at the travel time, you look at the 40-mile trip people, right? We're saving them 50 to 60 minutes, right? You look at the 20-mile trip people, we're saving them about 20 minutes. The 60-mile people, you know, they're being saved about 80 minutes. Right? So there is a significant impact on the vehicle miles traveled. You know, so if you look at it in terms of the VMT, you know, you move 1%, but if you look at it in terms of the VMT moved, it'll actually be larger than that, right? Because these are the longer trip people. And then, of course, if you look at the network, you know, this color is the busiest ones, and these are the less busy, and the grays are not busy. And the busiest airports are San Carlos, Palo Alto, and Hayward, exactly, which kind of makes sense, actually, right? Okay, then. Okay, the third network, right? I just looked at, I said, let's forget about the air side, right? Let's put in lots of vertiports and see what happens And, how many, is there a diminishing return and stuff like that? So let's go to the next slide. And here we actually do a hierarchical network design. Because what happens is, if you put a lot of vertiports, you reduce the first and last mile time, which is good, right? Which means more people will use your stuff. But you're spreading your demand across many, many vertiports. So your ability to consolidate people into an aircraft starts to go down because every arrival process has a low rate. And these people, of course, want to go to all the destinations in the world. So they get on different aircraft. So you start flying lots of aircraft with one person in. So that's why we do this hierarchical network design, where we create like these sort of zones, which are fully connected to each other. And then inside each zone, we put a number of vertiports. There's a second reason to do that too. We put a number of vertiports, but those vertiports, every vertiport is not fully connected to every other vertiport. So if you want to go to that destination, this is your closest vertiport. That there may be no flight from there to that destination. So you got to go something further. You lose on the first and last mile, but you gain on the load factor, right? So that's the trade-off that this is done for. And the other thing that happens is you can't build big vertiports. We'll see that in a slide. And you can see that actually this is here. So 10 zones. This number is about 80 vertiports, 76 vertiports. It produces a 6% VMT reduction. Right, so you build 80 small vertiports, right, over 10 zones, and you reduce 6% of regional VMT. Now, in this analysis, I have no SI constraint. I do have, no more than one operation per minute on a TLOF, right? That's used to size the vertiports or develop the number of vertiports. But I don't have there's no SI analysis of congestion in the air and all of that, right? None of that is there.
So I have a question.
Yes.
So the number of vertiports, is it at existing airports or are you also considering?
No. Here I'm assuming I can place them where I like. Wherever it suits me in order to increase the number of people who want to use UAM.
But that's not realistic, right?
That isn't realistic, right? But what I'm getting at is if you want to serve all the people in the world, right, how much can you get? Because, before we get to all these problems, right? Actually, why don't I hold my answer for a minute, right? Okay, then let's go to the next thing. So, though we didn't study SI congestion, SI air traffic control and all of these large numbers of flights, we did study the roadside congestion. And big vertiports are a really bad idea. Uber shows these big pictures, but the roads cannot handle the traffic moving in and the road traffic moving in and out of the vertiport. So this is the main reason why we then ended up, said, oh, we have to build lots of small vertiports, right? So this gives you, we've analyzed exactly which roads in the Bay Area improve, which ones get worse, et cetera, et cetera. Next. And, this sort of shows that as you get a larger number of vertiports, there are diminishing returns, right? And you're moving large numbers of people, and I'll comment on that later. Next. So do I have time for my generalizations? So that's 50. Next. Okay. So one is, I believe, based on my study of the air taxi cases, right? I am cautiously optimistic. I think the air taxi technology should find a foothold in the air transportation market and, in the two-airport transportation. And it is, I think, a significant market. Like if I just back of the envelope like this, 800 million, 10% traveling 20 plus miles, $5 per mile, it's an 8 billion market. Is that a large enough market for these companies that are capitalized in the billions? I don't know. That's a good question. These companies are heavily capitalized. And I don't know if this market is large enough for these guys. But this is, go back, right? And I do actually want to look at other markets. I want to look at the New York market. I want to look at the Bay Area market, maybe the Dallas market, right? And we are looking at the New York market ourselves, but it'd be great to partner with people to these markets and model how the operators will behave, et cetera, whether the kind of perverse incentives need to be corrected by some kind of policy reform, right? Where, you know, like a colleague of mine is studying that in cities where Uber doesn't want to go, instead of the city subsidy, you know, paying for bus services and a lot of money, should they offer an extra incentive to Uber and say, if you pick up that passenger, the passenger will pay you $8, I'll pay you another $5. Right, so he's studying exactly what kind of mechanisms, et cetera, can enable that kind of thing. And maybe this kind of policy thinking is important for the air taxi industry as well. But he just woke me up to that thought. So, you know, anyway, I shouldn't speculate too much. Next. So, you know, we all know this, right? I think this was in the NASA's RAM study, that the nation's airport network has a supercritical core and a subcritical periphery, right? It's a very small number of airports. So I do think that AN is a regional airport opportunity. People think these airports are in the wrong places. I think they're not. They're in, at least the airports are located to serve as many people as BART. Right? Next slide. A lot of this was motivated by NASA's RAM work, right? Many cities have a lot of airports. Next slide. Can RAs move 1% of urban mobility? Okay, I come up with 5,000 flights, right? Today, I don't know, there are 1,500 to 2,000 operations in Bay Area airspace, right? And I'm asking for, I don't know, 2.5x. But if you want to do this in eVTOL, the same volume, you'd be moving 58,000 flights. That's not doable.
You got one hand online.
I've got my hand online. Okay.
Michael?
Questions about San Francisco Bay Area when you said that you estimated that for 60 miles you found savings 80 minutes. This does not seem right because you at least if you are driving on highways, you can do 60 miles in close to 60 minutes. So how can you save more? Do you assume that some traffic jams on highways?
No, I think these are 2-hour plus commutes.
So it's not on highways. It's like
No, it's on highways. It's on highways.
But it does not match the distance. So you can do 60 miles in about an hour on highway.
If the highway is not congested.
Yeah. So that's what I am asking.
Yeah.
So did you assume?
And the trip data set gives me departure time, actually. Right. So I know exactly who's traveling in rush hour and who's traveling outside rush hour.
And my another question is that did you model that if more people switch to using UAM, this could maybe reduce some traffic in some spaces, but create more new choking points?
Yes, that's exactly why I had to, do this iterative simulation for a fixed point.
Okay.
In order to capture that, yeah. Okay, my next slide. So this is my answer to you essentially. That should we be flying bombardiers, for 15 miles? I don't know. My common sense says this is not very economical. But I do believe we are not going to see. I don't think the way to think about this is let's put up 80 vertiports in the Bay Area. I don't think that's the way to think about it. I do think the airports are the way to think about it. And I do think we have to build larger short-haul aircraft. Now, maybe you understand aircraft design well enough to tell me, Raja, that's impossible. You're talking rubbish. But my next slide is, at least some people did not think I'm talking rubbish. We have submitted a ULIP. We want to do conceptual aircraft design. I'm not an aircraft designer. We've teamed up with aircraft designers. We've started looking at what can we do for higher tempo operations at regional airports, which are turning them into SFO. And we've submitted a ULIP. This is Virginia Tech. It's University of Illinois. At least some of us believed that this is worth looking at. So I'm not trying to tell you you're wrong, but I am trying to say it's a problem worth looking at. I want to look at it. Next. 80 small vertiports can reduce VMT by 6%. That's good. 170,000 people in 45,000 flights. That's not so good. My analysis has no SI constraints. I think if I put them in, this whole analysis will collapse. Next. We know who these people are. Next. Right? Okay, we know who they are. Then, revolutionary modes of transportation reshaped civilization. We rebuilt all of America for the car, for the automobile. Next. And the transportation system has real problems, right? And what worked for the 20th century mobility is not working in the 21st. The automobile and limited access freeway very successfully opened land in the 20th century. We got the American dream. It's not able to do that now. We can't build new freeways. Next. LA County, 66 million passenger and freight trips. We give up 25% of county land for roads and parking. We pay a lot, and it's still become a bottleneck that we cannot get over. Next. We get problems like this, right? The Wall Street Journal writes articles of this kind. Next. And I would say to the administrator, who seems very interested in building aircraft, that this is an opportunity. Mr. Ford gave us a vision. It's lasted 100 years, but it's over now. Next. I think these aircraft are a better idea than airplanes. If the administrator is looking for a legacy, what better legacy than to outdo Mr. Ford? Let's stop him. Yes.
Presentation. Could you explain a bit more about your data set, how you plan your trajectory design within the ATC traffic flow?
Okay. What have we done with ATC traffic flow? So the only case study, right? Okay. So in the LAX case study, right, there we've considered the air traffic flow, right? There's some consideration in the regional airport one, the 24 airports, but let me speak to that. So there we actually, when the big problem is the approach to LAX, right? So, but we look at the Part 77 surfaces, we stay below it, we have clearance, we look at the helicopter routes, we follow those, and it turns out we placed our vertiport on top of the transit center in LAX, right? The roof of the transit center. That's why we did it. Downtown LA, we looked at, and there we actually did look at buildings and roofs and the convention center and the sports arena and the parking structure, and we picked something, right? Looking at, and we considered energy. So if you're higher up, it's good in some ways because you're flowing down to LAX, right? So we looked at all of this. So there we were careful. The big problem there was we wanted two routes into and out of LAX, right? So that the aircraft flowing in follow one route, the other one, but we couldn't do it. We couldn't, I don't know, maybe better people here who understand airspace better than me could do it. So there we actually had to design a holding fix where the aircraft coming out have to wait and the aircraft coming in, there's a separate fix, and then you have to sequence them, right? So that part is actually taken into account by the reinforcement learning, right? That because when the reinforcement learning makes bad decisions, aircraft hold for a long time, it gets penalized, and then when the simulations run again, the neural networks adjust. It's a actor PPO LSTM architecture. The neural networks adjust, and it starts to get better. So there we did that. In the regional airport case study, right? What we did is we maintained 5 nautical miles of separation between these aircraft. No, we maintained 3 nautical miles of separation between these aircraft, right? 5 would be ideal, but we couldn't make it. But we basically just said that, the everything is flowing from one airport to another. So we just said that there's a route like this, and we just keep 3 nautical miles of separation. If we cannot keep 3 nautical miles of separation, the aircraft doesn't take off. Of course. What we did not consider is, can I really design, there are these 24 things, right? So there are 24 times 24 interconnecting corridors. Can those all be separated? Will they delay each other? We did not consider that. Okay, so the kind of issue that came up where we can't get 2 routes out of LAX, aircraft on one route have to hold for the other route. We did not do that in that case study, because we were just trying to understand, are these regional airports decently located, right? So that's what we did. And of course, if you consider things like that, then, maybe the numbers won't be as optimistic, but it's a more difficult problem. Yeah, I think that answers your question. Yeah. So, we've done sort of different things, in different networks. We haven't really, there's a lot of things we haven't put together. Probably the most careful study is the air taxi study, because it was really the OEM trying to tell us that, hey, is this going to work? Whereas the others, we're just trying to sort of understand very specific points. This airport land just exists. Would it be useful for anything? And I want to make a case that we have to look at the airports. They are well located. And I am very worried that, these airports are a mess. I think I had this last slide, this EIPP thing, which we put together for this federal EIPP call that came out, right? We built this beautiful consortium. Caltrans is putting in money. I'll be the principal investigator if it gets funded. Joby's there, Arch is there, Whisk is there, the airports are there. These airports just sit there and say, if you can't answer all these questions, we're not going to do anything. And really, you're the guy who should be begging me to do something. This is your future. But these small airports, they are so badly resourced that the VCs might just do to them what Uber did. The city had all these taxis on medallions. The VCs did Uber bypass that whole infrastructure. This time, the VCs might just bypass these airports. They have no money. Every time they make an airport plan, it takes them 3 years to put something new in the ground. The whole, how do these airports raise capital? But anyway, I've become a real sort of airport and larger AAM aircraft.
Well, thank you, Raja. We really appreciate it. A lot of good discussion in the room as well as online. So I'll actually have to send you some.
Oh, I'd like to see the chat. Yeah.
I will send you the chat for sure. But since I'm a bit over time, I don't have to cut you off. But
let me say thank you to all the people who are online. Very kind of you.
Yes, thank you. And I could have said it better myself. Thank you, everyone, for attending the Airtime seminar. Please join us next week. We're actually hosting on Wednesday, the 18th at 11 a.m. with Mark Hansen from UC Berkeley. He will be talking about irregular operations, flight delay, and passenger delay, some new-ish evidence. So in the meantime, I will be dropping a link in the chat, and there is a QR code at the back for those who have feedback, more commentary for Raja, or generally ideas about what else we could talk about during the series. We would love to hear from you. Thank you all.